Hello, everyone. In this model, we're going to talk about P2P, the modular peer-to-peer networking stack. This is the agenda that we're going to follow throughout the presentation. First, we're going to explain why we started designing P2P in order to achieve decentralized process addressing. Then we're going to see how P2P is the perfect substrate for innovation, because we have the interfaces to move from models to innovation and back. Then we're going to explain and describe the core P2P models that we have currently in place in the P2P stack. And finally, we're going to see how having pluggable models allows us to enhance the features and the capabilities of our application with just a few lines of code. So P2P is a modular peer-to-peer networking stack. It gives us all of the composable routing blocks to assemble future-proof peer-to-peer networking layers. We will be able to run P2P on many runtimes, from browser to mobile phones to embedded systems. And it is the perfect substrate for innovation on new protocols, because the fact that we have all of the interfaces and composable models that we can put together in order to try new protocols and new applications makes it the perfect substrate to try new ideas. P2P is implemented in more than 7 languages, so we will be able to run P2P within Golang applications, JavaScript, Rust, and many others. P2P is built on the concept of decentralized process addressing. With decentralized process addressing, what we want is to have the ability to locate, connect, authenticate, negotiate, and interact efficiently with any process in the world, understanding by process, services, and protocols that are running in networking devices. We want to be able to do all of this independent of the runtime, so we don't want to worry about what runtimes the devices we interact with are actually running. We want to do it in a seamless manner so that we don't have to worry about NAT Traversal, heterogeneous networks, peers that are behind relays, and so on. Also, we want to be fully operational even in a case of mobility, relocation, or roam. So even if peers change location or even change networks, we want to be able to seamlessly interact with them with our protocols and services. And one of the key parts that allows and makes this feasible is that every peer in the network is going to be uniquely identified. So every P2P peer will be uniquely identified. So in the end, with this decentralized process addressing, what we have is a network and topology independent alternative to endpoint addressing. So the same way that we can access different services and protocols using the IP network, we will be able to do so with this decentralized process addressing in P2P, but with additional features, because we want in IP networks, if the service changes location, we need to use another endpoint to interact with it. And this is not going to be the case with P2P's decentralized process addressing. Where does P2P live exactly? It lives on top of the transport layer in the OSI model. Actually, it spreads a bit into the transport layer because it offers a transport models that has a common interface that the top protocols of P2P can leverage. And also it has a transport abstraction and transport factory to leverage existing transport protocols to establish new connections. So that's why we say that even if it's built on top of the transport layer, it spreads a bit because we also have in P2P a transport layer and a transport model that we're going to talk about. And this, on top of this transport layer of the OSI model, is where the transport model and interface is implemented. On top of the transport interface, we have the security model with the security interface, then the Moxer model with the Moxer interface, and then we have all of the application protocols that we want to build on top of P2P. Because in the end, with P2P, we have a modular protocol stack that fosters innovation through the design of new protocols and layers. So we will have the interfaces, we will have protocols that implement these interfaces and different models that we can compose in order to create new application or new protocols. At one point, we can foster innovation in several ways. We can come up with a new design of a new protocol that implements one of the P2P interfaces, or we can come up with a new interface, or we could even use these models in order to build new peer-to-peer applications. To give you a recent example of how we move from models to networking innovation and back in order to perform networking innovation, I want to illustrate this with a recent example. And the example is how we implemented a compression layer in P2P, because actually we were in the protocol side, so in the model side, we were exploring how compression could be used in order to improve file exchange in IPFS. So we implemented compression as part of the Bootstrap protocol. Then we realized that every P2P node could benefit from having compression. So that's when, from the models, we went to network innovation. We tried compression within P2P nodes. And so at what point in the stack it was better to put this compression layer, and then we came up with a new interface and a new model, a new compression model that with a single implementation, in this case JZip, that others could start leveraging. At one point, someone could come and implement their own compression application, and they could come up with a new layer the same way we came up with the compression layer. So we see that we have the perfect substrate in order to perform innovation. And the two key schemes that makes decentralized process addressing feasible are first peer identity and then the multi-addresses, that we're going to talk about it in a moment. Because as I've said, in P2P, every node is uniquely identified. And the way in which we identify them is through an ID that is derived from their public key. So every node is identified with a asymmetric keeper, and their ID is derived from their public key. We have several types. We support currently in P2P several types of keys. And the way in which we infer the ID from the key is in the following way. We use a multi-hash representation. A multi-hash representation is what you can see in the top of the slide. It's just a hash, the bytes of a hash of something with a prefix that specifies the hash that was used in order to perform that hash, the specific algorithm used to perform that hash. So in order to infer the peer ID, what we do is that we take its public key and we check its length. If the length of the public key is over 48 bytes, as it is, for example, the case for RSA, we need to hash this public key to accommodate for the length of our IDs. In this case, we use a SHA-256, we hash the public key, and we create the multi-hash, which in the end is just adding the prefix to specify that we hashed with a SHA-256 and the bytes of hashing, the result of hashing the public key with the SHA-256. If we use a public key that it is below 48 bytes. In this case, we don't need to do any kind of hash. And what we do is that directly the ID is the public key of the peer, and we add as a prefix what we call the identity multi-hash, which actually is saying that there is no hash and this is exactly the public key. So we are identifying the peer directly through its public key. So this is one of the key points that will allow us to have decentralized process addressing. And the other scheme is multi-addresses, because we need a way of having the contact information that will allow us to interact with other peers in the network. And we do this with these multi-addresses. These multi-addresses include all of the contact information that we need to establish a connection with another peer. In these multi-addresses, network processors are named as file paths. And in a multi-address, we specify all of the valuable processes in a peer in a single address. And this is what we use to dial the peers. So in the example that we can see in the slide, we're saying that for the IPv4 address 1234, in the TCP port 5001, we have an endpoint exposed for the peer for the P2P peer with a specific address. And with all of this information, we will be able to establish a new connection with this peer to which this multi-address belongs to. And with this, we are in a position to start explaining the different models of the P2P stack. Let's start with transports. As I've said, like transports in P2P, in the end, transports are core abstractions of P2P. So they are connection factories for communication between peers. It is what we're gonna use in order to expose the transport interface. So offer a way of the top level protocols to be able to interact with the transport protocols that establish the connection. And also this is what we use in order to dial other peers and to open, to listen to other peers in a specific port and a specific connection. So in the end, with this transport model, what we do is that we produce raw connections, socket, and sessions. So using a layer 2 from the layer 4, sorry, from the OSE model protocol. We currently support several transport protocols like TCP, QUIP, WebSocket, and WebRTC. So these connection factories, in the end, they will establish new connection and create new raw connections using any of these supported transport protocols. And in P2P, in order for two peers to be able to interact between them, they cannot do it through a raw connection. They will have to upgrade their connection in order to use security between them, so to establish a security channel between them, and to use a multiplex connection. And the process of going from a raw connection that the transport factory started with a peer to a secured and multiplex connection so that we can start interacting one with the other, we call this process the connection bootstrapping. So connection bootstrapping, in the end, what it does is to take a raw connection, create a transport, and upgrade it in order to use a specific security channel, so negotiate the security that we want to use between the two peers, and the multiplex protocol to multiplex different protocols over the same connection. And this is done dynamically. Some transport, like for instance, QUIC, can be used as raw connections because they already handle multiplexing and encryption by themselves. But in the case that we are running and we start a new connection, new raw connection that doesn't support multiplexing and encryption by itself, what we have to do between the two peers is run a protocol in order to upgrade our connections that is called multi-stream select. In multi-stream select, what we do is that we first perform a handshake. So we establish the raw connection with if we are the initiator, we establish the raw connection with the responder, and we send a handshake to specify the multi-stream select version that we are running. After this, the first thing that we do is we start the security protocol negotiation. In this security protocol negotiation, what we do is first we propose a security protocol to use to establish the security channel, and if the other peer doesn't support this protocol, it will answer saying that it doesn't support the protocol that it says. So first I may send and propose using TLS. If the other node doesn't use TLS, it will answer saying that it doesn't support that protocol. Then I would go to the next protocol that I support and that I'm willing to use for to establish the security channel. So I send a request for a message using multi-stream for, in this case, noise. And if the other if the other peer supports this protocol, it will answer echoing back the protocol ID. And now what it happens is that we start the security negotiation in order to establish the security connection. So we upgrade from a raw connection to a security connection. And the next thing that we need to do is upgrade the security connection into a multiplex connection. And we do the same. I mean, we use multi-stream in the same way that we did for the security negotiation to negotiate multiplex and choose a multiplex protocol that both of us support. If at one point when we establish a raw connection, we can't find a common protocol for the security channel for the multiplexer between the two nodes, the connection is terminated because we don't allow the connection, the communication between two peers in P2P if the connection is not secure. I mean, if we don't have a security channel and a multiplex channel. So if we don't both support the same security and multiplex protocol, the connection is terminated. And that's all for transport. Let's move to multiplexers, because we've seen that establishing a peer-to-peer connection may not be cheap or easy. We need to negotiate the security channel. We may need to perform hole punching or some kind of NAT traversal. We may need to do several handshakes. So in the end, we don't want new protocols used by our node to have to establish a new connection every time. And this is the reason why we use multiplexing, and we forced to use multiplexing connections between the communication of two peers so that protocols in a node can reuse established connections for several protocols. So applications will be able to leverage already established connections in the node. And this is really interesting. Streams. So we have several implementations of multiplexers available. We have language specific libraries for stream multiplex, or we can use transport protocol native multiplexing capabilities like in Quick. The way in which we identify messages from a specific, as we're using the same connection to communicate all of the protocols that are running within a node, the way in which we identify streams is using the unique identifier for streams that the multiplexer specification has. So according to the multiplex that we are running, streams are identified in several ways, but we have a way to know what message belongs to what peers, even if we're using what messages belong to what protocols, even if we are running the same connection for all of the protocols with the other peer. And we've seen that protocol negotiation is a key concept in libp2p. We did this multi-stream select, we run this multi-stream select protocol in order to perform the initial negotiation to establish the security channel and the multiplex channel, but we also need ways of identifying what other protocols and services the other nodes and the other peers are running for the case in which we want to interact with them. So once the connection has been upgraded, the first thing that we do is that, so once we have a multiplex connection, the first thing that we do is that we run what we call an identify protocol in order to identify the list of supported protocols that the other end is supporting. So we receive a list, running this and sending this identify message, we receive a list of the protocols after upgrading the connection and establishing the connection. We receive a list of the supported protocols of the other end. If at one point we still need to update this list after the upgrade, we can use a protocol that is the multi-stream list, that in the end, this protocol, what it's saying is that if we send a multi-stream list request to the other end will return the same way that it did with the identify protocol, a list of the protocols that it supports. So in this way, I will be able to identify what protocols the peers that I'm connected with are running. And another important concept for protocols is the way in which we identify protocols. Protocols are identified and protocol IDs are analogous to REST endpoints. So whenever we can see to the right some examples like pubsub / the version number, IPFS / Bootstrap / the version number. So in this way, we can identify and all of the protocols that a peer is running. And this is also used in order to understand what logic needs to be run when we receive a message for each of these protocols. So if at one point, for instance, I receive a message for the protocol ID IPFS Bootstrap and the version, what I would do is run the specific handler that knows how to process in the node, that knows how to process messages for that specific protocol. And in the same way, like implementing a new protocol within a libp2p node is really straightforward, because the only thing that we need to do is register a new identifier for a protocol, like for instance, to beacon change request, and then attach a handler to this protocol ID so that whenever we receive a message for this protocol ID, we know that we have to run the functions defined in the handler in order to process the message. And that's all for protocols and multiplexers. Let's move to security channels. Secure channels in the end are used for peer authentication and transport encryption. So as peers are uniquely identified and these identities are inferred from the public key, we want a way of knowing that we are establishing a connection with the right peer in the network. We also use the secure channel for transmission integrity, non-repudiation, and message authentication. For the security channels, we currently support, in the end, in the security channel, what we do is that we leverage our asymmetric keys in order to establish a new secure connection. So we negotiate a symmetric key that we will use for every interaction that we do with in that connection with the peer from there on. The use of security channels does not preclude from encrypting, signing application data. So application protocols will be able to use their own encryption and signing if they want, even if under the hood the connection uses a security channel and encrypts in the security channel for all of the communication of all of the protocols of the peer. And we currently support two main protocols in order to negotiate the security and establish the security channel, which are Noise, which is a security framework that performs the handshake and negotiation of primitives in order to establish the security channel, and then TLS 1.3, which is like in the end negotiate the security channel in the same way that it is done in the web. And with this, let's move to peer discovery, peer routing, and content routing, because we have models in libp2p also for this. For peer discovery, the peer discovery interface, what it does is that it exposes two main interfaces, an advertiser interface to announce services to other peers. So we will be able to let other peers know through this interface what protocols we are running, and then the discoverer interface that does the counterpart. So it finds peers which support a specific protocol. So in this way, we will be able to find a list of peers that are running the protocols that we're interested in. And the other way around, we will be able to announce other peers that we are running certain protocols. These interfaces, some examples of protocols that currently implement these interfaces are, for instance, MDNS, in order to find peers in our local network that are running certain protocols, or the Kademlia DHT. We can use the Kademlia DHT to find protocols that are running a specific, peers that are running a specific protocol. And we also have interfaces for content routing and peer routing. These interfaces were already introduced in the module dedicated for content routing. So if you want to check them in detail, I highly recommend watching that module. But in the end, these interfaces, what it will allow us is to first, for content routing, we will be able to find content address chunks of data in a peer-to-peer network. So it will give us the interfaces in order to achieve this, and also to find to perform peer routing. So to find the contact information in order to be able to dial peers. So all the main protocol that implement these interfaces currently in libp2p is the Kademlia DHT, our implementation of the Kademlia DHT. But again, as I already introduced in the model for content routing, we could use these interfaces and any other of the libp2p interfaces in order to implement other protocols implement other protocols with these interfaces so that it can be leveraged by libp2p nodes. So we could think of implementing these interfaces with a DNS protocol so that we are able to find this information from a DNS system. We could think or design a protocol that implements these interfaces and communicates with BitTorrent trackers in order to get information from BitTorrent trackers for content routing and peer routing, or any other providing subsystem. So in this way, we would be able to innovate in content routing and peer routing, leveraging the existing interfaces. And libp2p also includes schemes in order to perform NAT Traversal. Because the goal with the NAT Traversal protocols and interfaces in libp2p is to achieve global connectivity in a heterogeneous network. And we have three different protocols in place to achieve this. First, we have AutoNAT. With AutoNAT, what we do is that we request information from other peers to identify how is my network observed from the outside. So I send a request, an AutoNAT request, to nodes outside my network in order to know how it is seen, how am I seen from public networks. And in this way, we will be able to determine if we are reachable and if we are reachable with what specific address, so that when we announce our multi-address, we announce the multi-address that can be seen from public networks. So the result of this AutoNAT can be that we are accessible from the public, that we are in a private network that others cannot reach, or that the other peer was unable to identify what was my specific situation. So this is AutoNAT. If AutoNAT fails, we can always use auto-relay. In auto-relay, when a peer is not reachable from a public network, what we can do is first try to find a relay peer automatically. So when we run auto-relay, we try to find a relay peer automatically, we connect to them, and from there on, if we're able to connect to this relay node, we announce in our multi-address the address of the relay, so that from now on, whoever wants to connect, if someone wants to connect to me, they will check my multi-address, and the address of the relay will be included in the multi-address. So they will know that if they want to contact me, they have to do it through this relay. The problem with auto-relay is that it doesn't scale. First, if there are a lot of peers connected to the same relay and all the traffic has to go through that relay, this relay may be a bottleneck. But not only that, like, in order to achieve global connectivity with auto-relay, we need to deploy relays a relay infrastructure throughout the whole globe in order to enable the running of auto relays. So that's why this doesn't scale. But fortunately, we have also decentralized hole punching. With decentralized hole punching, what we try to do is that we use relay servers as a conduit for hole punching signaling and synchronization. So what we're going to do is that whenever we realize that we are private and we want to perform hole punching, if we want to reach another peer that is in a private network, what we do, and we know that it's private, so it's not reachable from a public network, what we do is that we first find a relay near the target. So we're going to try to find some temporary node to use as relay in order to that is able to reach the other peer in order to synchronize the hole punching. We also detect the NAT that the other peer is running in order to know the specific hole punching protocol that we need to run. So we go to the relay, we check the NAT of the other peer, and we try to run a hole punching protocol in order to establish and upgrade a direct connection to the peer. So comparing to the case of auto relay, in hole punching, what we're doing is that instead of using the relay for all of the communications with a peer, we only use it to perform the hole punching and establish a direct connection with the other peer. And from now on, we can interact, the two peers, my peer and the peer that is behind the NAT, can interact seamlessly with a direct connection. And finally, in P2P, we have also a pubsub interface. For those of you that are not aware with how pubsub algorithms work, pubsub is a message-oriented communication pattern. It is an end-to-end interaction model for asynchronous communication. So in the end, we have peers that will congregate around topics. We will have some peers that will be publishing messages for certain topics, and then other peers interested in these topics that will want to get this message delivered. So this pubsub paradigm is common in enterprise software, but when running these kind of protocols in the enterprise, they usually have decentralized brokers that are in charge of orchestrating all of the delivery and broadcast of messages to peers that are interested in a specific topic. The problem is that if we want to run decentralized and trustless peer-to-peer pubsub algorithms, we cannot have a broker, so we need to run brokerless protocols that are self-regulating and where peers have no global knowledge about the overall of the whole network. So the way in which we achieve this is that these protocols, they construct an overlay in order to collaborate for message delivery. So we will have peers that are interested in the same topics that will will create an overlay in order to collaboratively, whenever someone sends a new message, deliver it to all of the peers that are interested in this, in the message for this specific topic. So in this way, these overlays are self-regulating and are the ones that overcome the role of the broker that we had in centralized setups. We have several protocols available for pubsub in P2P, being the main ones gossipsub and flotsub. And the kind of use cases that we will be able to approach with these pubsub protocols are, for instance, IPNS, a way of sharing information about mutable content and content that have changed in a content address network. We can also use it for content addressing, so peers organized that are interested in the same kind of content, organized in the same topic, so that they receive information about where the content is stored. For blockchain consensus, pubsub algorithms are also used for message dissemination. So there are a lot of use cases for which pubsub algorithms are interested, and decentralized pubsub algorithms are really, really interesting. And finally, to wrap up the model, I wanted to give you an overview of how the pluggable models in P2P work with a practical example. So P2P models are plug and play, so they can be easily added to an application with just a few lines of code. So if, for instance, we want to start using P2P in our application, we need to start a new P2P node. And we can start a new P2P node, as we can see with these lines of code, where we say that we want to start a P2P node with that supports this specific transport with these Maxor protocols and this security channel. And from there on, we can use P2P. We can use this node to interact with other P2P peers. But what happens if at one point we need to do content routing and peer routing, or even content discovery. So it is really easy to include these features to our application through P2P by just leveraging one of the models that we have for content routing, one of the protocols that we have for content routing, and peer routing in place already in P2P. Because the only thing that we have to do is that we initialize, I mean, if for instance, we want to use the DHT for content routing and peer routing, we just need to instantiate this DHT. And when we start the P2P node, specify that we want to use this specific model. So we see that models are pluggable, and enhancing the features and the capabilities of our application using P2P is really straightforward. So that was all for me. Thank you very much. Please do not hesitate to reach out in case you have questions, comments, or suggestions. Thanks.